tell you why that name in just a moment. Okay, and so this is sort of a very geometric definition of pseudodifferential operators, just things whose Schwartz kernel look like this. The index m refers to a more precise description. So remember, what we did is we, at any point of the diagonal, I sort of localized. I chose local coordinates. I could cut off here, it doesn't really matter, and then I take the Fourier transform in this direction. Okay, so remember the way I thought about that was, for example, I could rewrite k sub a as a function of z and z minus z tilde. So that corresponds to taking a slice where I fix z and then z minus z tilde. It looks like that. So I can fix any transversal I like. Okay, then I take the Fourier transform. So I think that is w and eti minus I w dot zeta dw, and this is a symbol. This is a symbol of order zeta, and the m refers to this being a symbol of order m. Okay, so if I sort of try to describe this, of course, it seems a bit awkward, but basically, if I have a symbol of order m, then that's going to correspond to some particular growth order or some particular type of singularity here. As I let m vary, I get different singularities. Now remember, the model for all of this was just the Newtonian potential, just the Green's function for the Laplacian, right? So in fact, what one can show, now, typically, these conormal distributions, there's a slightly more special class, which is very convenient to use. So there's a special subclass, which is kind of easier to think about. And this is called, so it has this kind of ungainly name. PHG stands for polyhomogeneous. Let me just tell you what polyhomogeneous is in a special case. So this is just a subclass of conormal distributions. So remember, just things that have this sort of regularity. And it exists on any manifold with corners. So let me just first start on the real line, R plus. I have the variable x. Let me tell you what a polyhomogeneous distribution is there, and then we'll generalize from that. So if I have u, which is polyhomogeneous in R plus, what this means is that u is conormal. So that means, in this case, I can differentiate with respect to x d by dx. For any j, I can differentiate it 500 times, and it stays in L2, for example. I might as well assume that it's 0 out beyond 1. I'm only interested in the singularity near 0. And then this extra moniker, this polyhomogeneous, means that it has an asymptotic expansion. So it goes from 0 to infinity, where I'm going to have these coefficients in here. So it has an asymptotic expansion involving possibly fractional powers of x and positive integer powers of log x. Okay? And to be a little bit more precise, for every j, for every x to the gamma j, I have finitely many log terms. Okay. Now, why do I pick this special class? Why do I have positive integer powers of logs and so on? And the answer is, this is what kind of very generally arises as solutions to this class of degenerate elliptic partial differential equations. So the reason we pick this is that this is kind of a very natural class that arises in 5,000 different applications. Okay? But the important thing here is that you have fractional powers, you have non-integer powers. So to demand, and this is something that you see very often in classical literature, that they'll solve a problem, go to great hard work using classical techniques, and they say, well, this problem is the solution is only C2 alpha every alpha less than 1. And in fact, what happens is that there's a term that looks like x cubed log x in the expansion. So there are a lot of problems like that are kind of people have studied, and they're very smooth in this sense. You should think of this as just being like a Taylor series. It's as easily manipulable as a Taylor series, but it's you have these funny exponents. Okay, so we'll see some examples of that a bit. Okay, so that was polyhomogeneous on a manifold with boundary. Excuse me, on the positive line. If I have an upper half space, so just to refute Alice, x is the normal variable Alice. I know you really don't realize that, but so and here we have y in the boundary, and now it's PDE convention versus. So then, if I have something that's polyhomogeneous in x and y, what that means is it has once again an expansion that looks like this. where these AJLs are C infinity. Okay, notice that that's exactly, what are the conormal vector fields here? What are the tangent vector fields in an upper half space? They're things which are sums of objects like this, x d by dx and d by dyj. So if I have stable regularity with respect to d by dyj, that means that these things can't get worse when I differentiate them. They're smooth. Okay? But x dx, and just again, if I take x to the gamma and I take x dx of it, it just looks like gamma times x to the gamma. It's no worse. Okay? So this is these polyhomogeneous things are a special subclass. They're more easily manipulated, and it's a very small subclass within the space of conormal distributions. So maybe just as a brief aside, what does a general conormal distribution look like? Well, here's kind of a description. So if I were to take the following, suppose I would take x to the gamma, and some domain, and then I integrate with respect to any measure of gamma. So I'm integrating with respect to the exponent. Anything like this is conormal. And basically saying you're polyhomogeneous says that that's an atomic measure. Okay, so you can work with stuff like this, and it's kind of hard to find things like this in nature. I mean, you can write them down easily, but to find a PDE where these are kind of, when you have a more general measure, I know PDEs like that, but they're not very natural.
What measure is it? An atomic measure?
Excuse me?
An atomic measure?
Yeah, so if like d sigma of gamma is a sum of delta functions, then you get something like this, right? Or deltas and delta primes and so on, then you get something like this. But in general, it could be like Lebesgue measure or, any singular continuous. I mean, it could be crazy, and you'd have a conormal distribution.
I don't understand. Is the quite an integral or gamma?
Just that, you integrate over the exponent. Suppose I were doing this with respect to Lebesgue measure. I'd look at e to the gamma log x d gamma, and that would be, say from 0 to 1, I'd have like 1 over log x. That's a particular case. So you can get all sorts of things like that. Okay. I mean, you can create a lot of crazy functions, and they're all conormal. Now, where does the name conormal come from? I owe you an explanation for that. So the word conormal, so associated to any distribution, something that you all know and love is its singular support. So the singular support of u it's a closed set, and it's exactly the place where the distribution is singular. So it's usually defined by, you have a distribution defined here in some open set. There's some possibly very messy closed set, and away from there, this distribution is represented by a smooth function. Okay, so that's a classical thing you learn in distribution theory. So there's a refinement of this, which is called the wavefront set. And it's defined in a good way. So I know that you guys are all coming from very different backgrounds, so you may not have seen this. So let me just remind you what it is, because it's a fundamental concept in microlocal analysis. And if you're doing not elliptic PDE necessarily, but hyperbolic PDE, this is like a really crucial thing to study. It's really the generalization of Huygens principle that's sort of underneath this. So the wavefront set says, well, take a point. So now the wavefront set lives in the cotangent bundle, so it's really points and directions. So if I have a z and a zeta is in the wavefront set of U, let's call it z naught and zeta naught is in the wavefront set of U, what does this mean? Well, the definition is a little bit intricate, but basically what it says is, here's the point z naught. Suppose I take a cutoff function. So suppose I take a cutoff function to a small ball around that point. Okay, so chi is 1 at z naught and at 0 somewhere else. I multiply by u, and then I take the Fourier transform. Okay, so I localize and take the Fourier transform. Okay, so this is now a function of zeta. Here's the zeta plane, here's Rn sub zeta. And what can happen to this thing is that it's going to be, in certain directions, it'll be rapidly decreasing. And in other directions, it'll be slowly growing, or non-rapidly decreasing. And so the wavefront set is exactly the set of directions where when you localize arbitrarily much, it's not rapidly decreasing. Okay, so just as an exercise, suppose I were to have a hypersurface, a submanifold of any dimension, sorry, and I take the delta function along S. So this is a very geometric distribution, which means delta sub S paired with a test function, which is the integral along S of phi with respect to a nice smooth measure. Okay, it's a nice distribution. Where is the wavefront set here? Well, if I localize, then this thing is essentially linear, right? So I might as well, approximate, think of it as a line. So here's RK, here's Rn minus K. So I'm thinking of U as a function of Z prime on Z double prime. So here's the Z prime, here's the Z double prime variables. If I take the Fourier transform, and this is along Z double prime equals 0, that's this is a manifold, right? And I have, so this is, so really what I'm doing is, of course, I'm just, multiplying, so I should really put in a 1 times a phi of Z prime, a chi of Z prime. So I'm integrating along the submanifold density 1 that I've multiplied by a small cutoff function. Okay? So what's the Fourier transform of this? I'm integrating it to Z prime. Well, so the point is if I integrate the function chi of Z prime, that's going to be, so this thing is going to be, so let's say U hat of zeta prime and zeta double prime. So in the zeta prime directions, it's rapidly decreasing. So here's the zeta prime and zeta double prime directions, the Fourier transform variables. In zeta prime, this is just the Fourier transform of a compactly sorted smooth function. So in these directions, it's rapidly decreasing. In fact, if I go off in any conical direction, it's rapidly decreasing, except for when you go up or down. So if you go in the zeta double prime direction where zeta prime is 0, it's constant. Okay? So that's really the fact that the Fourier transform of the delta function in Z double prime is the function 1. Okay? So the wavefront set of, well, let me say it invariantly, the wavefront set of this thing is the conormal bundle of S. Okay, conormal. That's why we call it conormal. So it turns out that in general, the wavefront set can be, it's a closed conic subset of the cotangent bundle. It turns out that naturally it's a subset of the cotangent bundle, so there's a lot of good geometry behind there. And this class of conormal distributions are exactly the things whose wavefront sets are in the conormal bundle of the diagonal. So that's the reason for all this. Okay, so let me tell you a fact about elliptic operators, which is not necessarily thought of in these terms if you're thinking sort of more classical styles, but let me tell you sort of a familiar fact of elliptic regularity and then a slightly non-familiar fact about elliptic regularity. So here's a fairly easy fact. So if A is a pseudodifferential operator, which is elliptic, this is a purely local statement, by the way, so I don't worry about manifolds compact or anything. So if I have an elliptic pseudodifferential operator, which just remember means that its symbol is greater than or equal to C times 1 plus mod zeta to the m. Okay, and if A of U equals F, then the singular support of U is equal to the singular support of F. So in some sense, you always think of elliptic operators as things which makes things better. Well, I do at least. But in fact, this is exactly the reverse. It shows that elliptic operators are the things which don't make things better in a maximal way. In fact, they preserve singular support exactly. So in other words, if you have a point in the singular support on this side, it has to have already been there to start off with. It can't destroy singular support. So in fact, there's sort of a corresponding statement. So let me just say it this way. The wavefront set of U is also equal to the wavefront set of A of U. And now there's a slight flip. So union the characteristic set of A. So if A is elliptic, so this is empty if A is elliptic. Okay, so if you have an elliptic operator, the wavefront set of U and the wavefront set of A of U are exactly the same. Okay, if A is not elliptic, if it's like the wave operator, well, so suppose you have box U is equal to F, where box is the D'Alembertian, it's the wave operator. suppose that f is the delta function at the origin. What's the wavefront set of the corresponding solution? Well, it's the light cone. There's your solution U, or some subset of the light cone. So this is in fact exactly what happened. The wave operator kills all of that wavefront set, and the outcome is just singular at the origin. Okay, so I couldn't pass that up without saying that. It's not part of the related to our main theme, but I wanted to say that. Okay, so let's get back to sort of geometry and some of the applications we're interested in. So I've talked about, all of this setup and said some of this is local, some of this is on a compact manifold. Now, what happens when M is open? What can you do? Okay, so the first thing is, so I said you can always define pseudodifferential operators on M in exactly the same way. They're things whose, well, it's gone, it's on this other board, right? Things which are conormal on M cross M with respect to the diagonal. Okay, that always makes sense. However, the interesting operators that are closely connected to geometry, you have, so you're going to have these k sub a of z and z tilde. These are distributions in M cross M. And what we're really interested in, and is very profoundly affected by the geometry, is not what they're doing along the diagonal, which is now kind of universal. I've told you everything that happens along the diagonal for any pseudodifferential operator. And forever after, when we talk about pseudodifferential operators, there's some singularity there. You know exactly what it is. We don't care, right? I mean, it's just the same thing no matter what the geometry. What's interesting is what happens when you go a long ways away from the diagonal, so the so-called far field effects. And this is very different for different sorts of geometries. So I'm going to illustrate this by recalling some of Alice's examples, or some of the cases she's been talking about the past few days in the asymptotically hyperbolic case, because you see one particular type of effect. But there's kind of an adapted pseudodifferential calculus for every sort of geometry, and it'll tell you different things. Okay, so I'll try to give a few examples of that. Okay, so let me sort of say that. So given any, let's say, geometry, there is an adapted pseudodifferential calculus. And the reason for developing these things is because if you're interested in global effects, and so, for example, with Alice's theory, she talked about scattering theory, or she talked about sort of perturbations of Poincare-Einstein manifolds, things like that. They all correspond to, things you want, that would be, applications in the pseudodifferential calculus associated to an asymptotic hyperbolic manifold. If I have an asymptotically Euclidean manifold that appears in many other types of geometric applications, there's completely different phenomena that happen. But there's a pseudodifferential calculus that can handle this. So this sort of local or compact theory is good for studying all local problems. But if I want to study a global problem, this is kind of an extremely good tool for it. So that's kind of the message from the calculus. Okay, so let's take our let's say main example for these lectures, at least for today, is, okay, well, I'm going to sort of approach it in a very non-geometric way, and then I'm going to show how it corresponds to this asymptotically hyperbolic set. Okay? So there's going to be a class of degenerate operators which arise in a lot of applications, and let me tell you what they are. So there's a class I'm going to call this diff zero star. Okay, so here M is a manifold with boundary. So again, I choose X and Y are my boundary coordinates, and I'm going to describe a class of differential operators on this manifold with boundary, and here they are. So it's anything of the form. So I'll write this as AJ alpha of X and Y, X d by dx to the J, X d by dy to the alpha. And these AJs are, and this is, let's say, order n. So some positive number. Okay, so those are differential operators, okay? Why would I study things like this? So first of all, notice that in the interior, they may be perfectly nice, but this form of this degeneracy means that when I get to the boundary, it's really completely degenerate. Okay, so here are some examples. For example, I could take, x squared dx squared plus x squared times the Laplacian of y plus, a times x dx plus a sum bj x dyj plus some c, where the a, b's, and c's are all smooth functions. So when I go to the boundary, x equals 0, everything's disappeared except for the c. Right? So they're called totally degenerate. They're called zero operators because everything is 0 at the boundary. Bad name, right? So why would we bother considering operators like this? Well, because there's a lot of interesting problems that involve them. So let me give you 2 or 3 examples. 3 examples. So the first example is one that I mentioned. In fact, the first 2 examples I mentioned the other day. So first of all, if I have the Laplacian in hyperbolic space, I use the upper half space model of hyperbolic space. I'm taking the scalar Laplacian. I am going to have x squared times the Laplacian in the x and y variables plus 2 minus n times x dx. Okay, it lies in that class. I can take other natural geometric operators. So I can take the Dirac operator, I can take the Hodge Laplacian, I can take the Lichnerowitz Laplacian, etc. So you take any natural geometric operator, it's always of this form. How do I describe this form, by the way? Well, so I look at, once again, the thing that you start off with is a generating set of, so this is the span over C infinity of x d by dx and x d by dyj. So I take the vector fields which are vanishing at the boundary. So this is a nice geometric coordinate-free thing. This is all vector fields in the interior which are smooth. They do whatever they want in the interior, but at the boundary they're 0. And I take the span of these. So I just take arbitrary sums of products of these things with smooth coefficients. And these operators are exactly the things that are formed by these. Okay. Okay, so on hyperbolic space, I have all of these examples. More generally, if I have a conformally compact manifold, so exactly in the form that Alice was talking about, I'll be with different notation. So I have a compact manifold at boundary. I have a G bar as a metric, which is non-degenerate up to the boundary, and rho is a defining function for the boundary. So like these conformally compact Poincare-Einstein metrics that she's been talking about. So I take any manifold like this. Any one of these geometric operators is one of these 0 operators. Okay, so that's another big class. Okay, next case is, well, I mentioned this on Tuesday. I take any non-degenerate operator. So let's suppose I take, a sub j alpha of x and y times dxj dy to the alpha, j plus mod alpha less or equal to m, and then I multiply by x to the m. So I take any perfectly nice non-degenerate operator, and then I destroy its non-degeneracy by multiplying by the order of the operator. Okay, I can rewrite that by putting it, so the point being that I have as many powers of x as I have derivatives. Now, any low order term then is going to have a higher order power. So in a certain sense I'll be describing, it becomes sort of really a negligible term near the boundary. But at the boundary, you're going to see sort of principal terms, and all the low order terms are going to have too many powers of x. They become low order. Okay. And then the third example, and this kind of really gets to the theme of this whole week, which is fractional Laplacians. So the Caporelli-Silvestri extension problem. So suppose I have Rn, and I wanted to find the powers of the Laplacian to the s on Rn. So I'm going to choose a variable here, which I'm going to, well, let's call it v still. So I let Rn be the boundary of Rn plus 1 upper half space. Okay? And I form the following operator, L sub s, which is equal to dt squared plus 1 minus 2s over t dt plus Laplacian to 0. Okay. Now, this doesn't look so bad, but of course it has this coefficient here. So this is just sort of one of these 0 operators in disguise. So I'm going to factor out a t to the minus 2, and what's left over is t squared dt squared plus 1 minus 2s times t dt plus t squared Laplacian 0. So that's examined in that form where t is the boundary defining function and z is only one boundary. Okay. So what the Caffarelli-Silvestri theorem or method tells you is the following. So if I want to define Laplacian to the s, sorry, I'll forget the minus sign there, so I'll just write this Laplacian to the s. So if I take Laplacian to the s of u equals f, how am I supposed to interpret this? So here's their prescription, which is really a subclass of the scattering theory for these guys here, as I'll explain in a few moments. So if I take Laplacian to the s of u equals f, this means find a function capital U of t and z in Rn plus 1 plus. Okay, so that capital L sub s of u equals 0. Okay, so I solve this equation where capital U of 0 comma z is equal to little u of z. So this is the boundary value of capital U. The general theory, which I'm going to talk about for this class of operators, says that capital U of t and z has an asymptotic expansion. So it's going to have an expansion of the form uj of z t to the j. J goes from 0 to infinity, plus some L goes from 0 to infinity of Vj of z times t to the 2s plus j. Okay, so there's a fractional exponent. So that's an example of a case where I have a naturally occurring flat fractional exponent. I'll tell you where that comes from in a few moments. Okay, so this is an actual theorem, right? It's not just a guess. It turns out that any solution of this equation always has an asymptotic expansion that looks like this. The caveat is that this may not be a classical expansion in the sense that these UJs and VJs may not be smooth. Right? So it's not like a smooth Taylor series, they may be very distributional. Okay, and then V0 is by definition the fractional Laplacian of U0. So this is that. Okay, so that's the Caffarelli-Silvestri definition via Fourier transforms, or via this extension method. Okay, so it's sort of buried in here. I have a zero operator, and you want to think of this as being like a Dirichlet denoting operator. So again, this is very much like what Alice talked about today. U0 is the Dirichlet data, and V0 is the Neumann data. Okay, and you can characterize this V0 in the following way. I can take d by dt of capital U, that's going to kill the leading term here, and then I take the limit as t goes to 0 of t to the 1 minus 2s of this side, and that's going to equal this V0. So this is like the Neumann derivative. Okay, and it's kind of, it's occurring, it's the t to the 2s coefficient which you're thinking of here. And just to show you that this limit's really well defined, in this particular case, and it's purely because these coefficients are so simple, it turns out that you only have even powers here. So if s is between 0 and 1, this limit is well defined because 2s is less than 2, which is the first coefficient. Okay, so I've told you 3 interesting examples, or 3 interesting classes of examples of these zero operators. So now I want to tell you how we analyze them and what are the main results. And so what I'll be doing tomorrow in my final lecture is talking about the fractional Laplacian on subdomains of Euclidean space. And so what I'm interested in, the things I'm interested in currently is what can I say about fine boundary regularity of solutions of Laplacian to the s of u equals f when you're on a bounded subdomain. Okay, and this is going to be an extension of this theory where I don't have a simple boundary, but I also have like an interface on that t equals 0 subspace. So that's a new singularity. Okay, so we have a class of operators and a class of vector fields that they sort of correspond to, and there's an underlying geometry, which is this hyperbolic or asymptotic hyperbolic geometry, which is all kind of inspired by. So let me just say that very briefly. So I have these vector fields, V0, which I've written down here, these 0 vector fields. Any vector field in here has bounded length with respect to the Euclidean, well, with respect to the hyperbolic metric. So dx squared plus dy squared over x squared. or indeed any conformal compact metric. So a way to have done these is to say, take this hyperbolic metric, or any asymptotically hyperbolic metric, and take the smooth vector fields, and vector fields which are smooth up to the boundary, whose length is bounded. So they have to decay at least like X. They could decay faster, right? But all of these bounded length vector fields with respect to this metric are the subclass I'm interested in. And this kind of explains why the Laplacian has to be one of these operators, right? Because it's a sum of squares of unit vector fields. I mean, that's sort of how you define the Laplacian, essentially, is you take second covariant derivatives in every direction, right? With respect to an orthonormal basis, with respect to the hyperbolic metric, or the orthonormal basis of bounded vector fields. Okay, so in some sense, this hyperbolic geometry is underlying each of these three examples. Okay, so what we're interested in, so we want to find parametrices. So we want the following. One is to find parametrices for elliptic elements. For elliptic operators in this class. We'd like to understand regularity theory. So what can you really say about solutions of L of U equals F near X equals 0? What's the regularity theory? And right, and then various applications of these. But so these are kind of the main analytic things that you might be interested in. Well, mapping properties, I guess, right? Global mapping properties. Okay, well, you should have already complained at this thing, because I take one of these operators, oops, I erased it. Take one of those operators. There's no way it's elliptic, right? I mean, it looks terribly non-elliptic at the boundary. So we have to invent a new notion of ellipticity. So this is, well, I'm going to call it zero ellipticity. Okay, and so basically what I'm going to do is mimic. Now I'm going to do something that's very coordinate dependent and then tell you that it actually has an invariant characterization. So I have these I have X and Y. I have these vector fields X dx and X dyj. And I'm going to formally replace every X dx with XC and every X dyj by an A to J. So these are supposed to be like cotangent variables. But notice I've sort of omitted the factor of X. So X dx is like a single unit and it gets replaced by C. X dyj gets replaced by A to J. So when I do that, so this operator, let me write it down, A j alpha of X and Y, X dx to the J, X dy to the alpha, J plus mod alpha is less than or equal to M. I'm going to replace it by its zero symbol, which is, I'm going to take the top order part, so that's equal to M, Aj alpha of X and Y, C to the J, eta to the alpha. Okay, so it looks like a formal replacement. So the fact, and this is, that Rod and I always talk about, so these C's and etas look completely artificial, but they're actually linear variables on a different bundle. It's sort of a replacement for the cotangent bundle. So there's some new bundle, it's called the zero cotangent bundle, for which these are linear variables. So this is a completely natural operation, just like taking the symbol as in the ordinary sense. Okay, and so ellipticity means that this new zero symbol is invertible. Okay, so in particular, if I look at the hyperbolic Laplacian, right, this guy here, if I have this x squared times dx squared plus dy squared, this gets replaced to c squared plus mod eta squared in this parlance, and that's clearly invertible. And it has the lower bound. So these are all good operators in this sense. So now I've described to you what the elliptic elements are. And there's a sort of a general meta theorem that any of the natural geometric elliptic operators in an asymptotically hyperbolic manifold are zero elliptic. So I take anything which just in Riemannian geometry is elliptic in sort of an ordinary sense, so like the Lichtner, it's Laplacian and so on, it automatically satisfies this condition. That's an easy meta theorem. Okay, so if I want to find parametrices, I have to know where to look, and that's why I told you the idea last time, which is I look at M cross M. So now I have variables x, y, x tilde, y tilde. So I'm thinking my ring function as a function of, this is case of A, as a function of, it starts off being a function of z and z tilde, that z is equal to xy, and z tilde is equal to x tilde y tilde. I picture m cross m as a manifold with corners. So here's y and y tilde is the corner, here's the x coordinate, here's the x tilde coordinate. Everybody see? So this is like a quarter space. So our problem is that this Schwartz kernel is a distribution on the quarter space, and there are a lot of weird distributions when you have corners or boundaries. So here's the diagonal. This is the diagonal. And we know at a very minimum that this distribution has to be singular along the diagonal with the standard pseudodifferential singularity order -2. That's just because, well, or order n. I mean, if I'm looking for pseudodifferential operators, nothing new is happening along the diagonal. The far field effect is what happens when x goes to 0, x tilde goes to 0, or maybe simultaneously if they're both going to 0. Okay, so that's what I have to describe. And so the idea was you blow up the submanifold x equals x tilde equals 0, y equals y tilde. Okay, why that? And I'll tell you in just a second. So what is blow up? Let me say it a little bit more carefully. Let's start with a simple case where I just have the quarter space, x and x tilde. It's just R2, the positive sector in R2. Okay, I want to blow up R2 plus, this is the notation with respect, I want to blow up the origin in R2 plus. So here's the origin, there's R2 plus, I want to define the blow up. So from a, say, a differential topological point of view, what I'm going to do is I'm going to remove this point and replace it by its inward pointing set of spherical normal vectors. So I have all possible unit length vectors which point into them. Okay, well that's just there's a quarter circle of those. So this is the space in first term. Now, more prosaically, I introduce polar coordinates, r and theta. R is sort of the distance here, theta is that angle, and I include the face r equals 0. So it's a quarter circle at r equals 0. So I'm replacing this point here by a quarter circle. Every point in this quarter circle corresponds to an inward pointing direction. Okay. Now, there's a natural sense in which I take any reasonable submanifold of a manifold with corners, I can blow it up, and I get a new, more complicated manifold with corners. Okay, so I'm going to do exactly this blow-up operation, but around that submanifold I talked about, which is the diagonal of the corner. So the corners were x and x tilde equals 0, and its diagonals were y equals y tilde. So really what I'm doing is I'm taking this space, I'll call it m2, 0, and I'm taking m squared, the manifold plus itself, and I'm blowing up at the diagonal of m boundary m plus boundary m. Okay, what that means is, I start with this space, here's this bad submanifold, or here's that interesting submanifold, depending on your perspective, and I blow that up, and I get something that has a quarter sphere here, and there's the diagonal. Okay, now this is just kind of a, I've introduced singular coordinates, so it's no big deal. There's a blowdown map, beta, and what we're looking for, so here's the ansatz now. So if I take psi 0 star of m, by definition, this is the set of operators A, linear operators, whose Schwartz kernel is conormal on this m2, 0 with respect to this lifted diagonal. Okay, so it's conormal on this whole space with respect to this lifted diagonal. Now, there's a big advantage here. This lifted diagonal intersects that face transversely, right? Here, there's no transverse intersection, so that actually screws things up analytically in a very serious way. So the fact that this intersection with a corner is bad is one of the reasons you do this. Here, you have a nice transversal intersection. Conormality, just our usual thing. We have a singularity along here. And let me put a little PhD here, polyhomogeneous. I look at classical things with expansions. What I'm actually requiring is not only is it conormal here, but it's conormal on this face, and on this face, and on this face. So it's smooth up to all boundaries. Okay, so remember, this is just a nonsense. I'm guessing that operators have this form. Okay, and so here's a theorem. I'm lying slightly, but not too badly, right? That if I have, let's say a differential operator is elliptic, right? Then there exists a parametrics G, which is an element of psi 0 minus M. Okay, so there's something of this form, so it's polyhomogeneous on this space here, and it's of order minus M. So the minus M tells you what the order of singularity is along here. Then I have some sort of expansions along these faces. Okay, so this is a definition, just we're hoping for some nice class of operators, or we define them. This kind of proves that this is a good definition. It says if I have something like the hyperbolic Laplacian or any one of these guys, parametrices live in that space. So that's the payoff. Okay, so what do I need to do to prove a theorem like this? Well, so the first thing is I want to show that this class of operators is actually nice, by which I mean I can compose things. So I'd like to prove theorems of the following form. If A and B are in the subclass, psi 0 star, then A composed of B is. And the orders add up. Okay. Now that's pretty non-obvious, in fact, because I have this really weird singular structure near the boundary of the corner. I'm saying if I take two of those operators with that same singular structure, then magically their composition does as well. So that's a real theorem. I mean, it's not that one, but it's a real theorem. So that's non-obvious. And then other things that you'd want to do is you'd want to prove that, for example, if A is any pseudodifferential operator of this type of order M, then A is bounded from, let's say weighted L2s. Well, there's sort of weighted Sobolev spaces. And from weighted polar spaces. U, C, K, alpha, 0, and so on. So I put a 0 here in the subscript here. Why do I do that? Because actually, the easiest bounding properties are with Holder or Sobolev spaces, which are similarly degenerate. They're sort of defined relative to the structure. So there's a whole yoga about how to do this, but the point is that if I were thinking about these operators, so, I've told you sort of the very coordinate-based definition. One way I can think about them is think about all these operators as living in hyperbolic space or asymptotically hyperbolic spaces. Then these would just be operators that have kind of very uniform behavior and have sort of nice expansions near infinity. These would just be the ordinary Sobolev and Holder spaces on hyperbolic space. X, so this variable x in hyperbolic space is like e to the minus distance. So if I take a point here and I take the variable x going to 0 means the distance is going to infinity from this point. So if I take the distance from this point to down here, then x is like e to the minus distance. You can check that in the Poincare upper half space. If I take the hyperbolic distance between 2 points, then that's behaving like the boundary defining function. Okay, so the point is that these are Sobolev or Holder spaces, which are defined uniformly with respect to the hyperbolic geometry, and they're weighted by exponentials in the distance function. So these are the properties that you'd like to prove, and you can. So there's some work to be done. And in some sense, we did all this hard work with the oscillatory integrals on Monday, and all that stuff just carries over verbatim. So you don't even need to talk about it. You just say it works. The new thing that you do have to worry about is why this sort of weird singularity structure at the corner happens, and why it persists under composition and so on. And so that's what takes work. So you have this sort of nice set of operators that compose well and so on. Then this theorem, once you've set everything up, is just exactly the elliptic parametrics construction that we did in the compact case. It just carries over to this case. So again, the reason why you go through all this kind of abstract machinery is that you have a sort of a set of ideas that work in the compact manifolds, and it just transports immediately once you have the right more general definitions, right? And you know, the reason this is good is that trying to do this by more classical methods is a lot of work. I mean, people have done it with various things, but it's a very awkward construction, whereas here it just becomes a very natural construction. Okay, so this is the parametrics construction. The interesting thing is what it tells you and what the regularity theory is. I want to sort of call a bit of attention to that because that relates to some of these applications like this fractional Laplacian definition. So this is now sort of more analytic side of things. So suppose I have one of these operators, L, which is elliptic. It's a differential operator, it's elliptic. So the first notion is what's called an indicial root. So these funny fractional exponents, where do they come from? Well, suppose I try to apply L to some power, L to x to the gamma. Okay, remember L is built up out of things like x dx and x dy. And if I apply an x dx to this guy, it stays the same up to a factor of gamma. If I apply an x to the gamma, x to the y, it gets bigger or smaller. It becomes x to the gamma plus 1. Okay, so, and of course, I mean, I have some smooth coefficient here. So in general, this is big O of x to the gamma. So for any one of these operators, you apply L to any x to the gamma, it stays the same. So you say that gamma is an indicial root if you get one better. So if there's some leading order cancellation. Now this notion should be familiar. So if you study Fuchsian regular singular differential, ordinary differential equations, this is sort of a 19th century notion. So in fact, what I'm going to tell you is sort of a big PD generalization of Fuchsian ODE theory. Okay, so for example, for the hyperbolic Laplacian, if I apply this to x to the gamma, I'm going to get, so this is going to give me gamma times gamma minus 1 plus 2 minus n times gamma times x to the gamma plus big O of x to the gamma plus 2, in fact, in this case, because there's an x squared plus 1. In fact, it's 0 because I have coefficient 0, but coefficient 1. So what is this? This is gamma times gamma plus 1 minus n. This equals 0 when gamma equals 0 or n minus 1. Okay? So in general, the initial roots are determined by, you know, the algebra of the coefficients. You get a quadratic equation, and you have to solve a quadratic. And of course, the solutions could be real complex, you know, whatever they are. Okay, so it's just determined by what are the coefficients. So it's just because I have such a nice operator that has integer coefficients, I get such simple initial roots. So the expectation is that if I have a solution to L, so if I take a general operator, I'm going to get a list of initial roots. So in general, if it's an mth order operator, an mth order scalar operator, I'll get m roots because I'm going to get an mth degree polynomial. If I have a 2 by 2 system of order m, I'm going to get 2m roots and so on. So I say this, so for example, the Lichnoritz Laplacian is, you know, a big system, second order system, and I'm going to have a bunch of initial roots. There's a lot of multiple roots in that case, but. Okay, so the expectation is that if L of u equals 0, then u should have an expansion starting with these initial roots. So u has an expansion that starts with, so let me write it as aj of y times the first initial root, 0, x to the j, plus bj of y times x to the n minus 1 plus j. So that's the expectation. And that's exactly what you get if you sort of formally guessed a series solution, plugged it in, and tried to make all the coefficients vanish. You choose the coefficients one by one. And what you'll find is that A0 and B0 are formally free. Namely, I can plug in any function A0 and B0 I want, and I can generate all the other coefficients as some sort of differential operators applied to these leading coefficients. Okay. Now, if I have an actual solution in the neighborhood's boundary, I'm not going to be able to do that. The analog is, suppose I just have the standard Laplacian, which I multiply by this. The initial roots are gamma is equal to 0 and 1. So for a non-degenerate second order operator, the initial roots are 0 and 1. X to the 0 corresponds to Dirichlet data, X to the 1 corresponds to Neumann data. So the two free coefficients are like here. So A0 is like the Dirichlet data. In this case, B0 is like the Neumann data. And so, if I have a solution formally, I can choose them to be anything I want. Locally, well, they're going to be kind of related, but if I have a solution globally, then there's going to be some global Dirichlet to Neumann mapping which says that B0 is going to be some operator, let's call it D, applied to B0. And D is in fact, it's going to be a pseudodifferential operator. In this case, it's a pseudodifferential operator of order n-1 on the boundary. So there's a generalization in this case of pseudodifferential operators, of Dirichlet to Neumann operators, and there's pseudodifferential operators in the boundary. So in the interest of time, since I have a short lecture now, I just want to give two very short examples, and then I'll expand on the second one in particular tomorrow. So one is related to this whole yoga of getting GJMS operators that Alice mentioned, and the other is related to the Kapfelli-Sylvester method. So I'll say those and then I'll stop. So there's a lot of details of this regularity theory, which I'm not telling you. And in particular, there's an analog. So think about the following thing. Suppose I have a domain, omega, smoothly bounded domain, and I have a non-degenerate elliptic operator, L0, and I take x squared times it. So I do this thing that I said, I can take a non-degenerate elliptic operator and apply and take x squared times it. What do I expect to be true of L of u equals 0? Well, there's two things that could be true. If I have a solution which sort of vanishes at the boundary, then this should be a theorem that you know and love from Gilbert and Truding or whatever, that if you have a smoothly bounded domain and an operator with smooth coefficients, which is elliptic, which satisfies Dirichlet conditions, it's smooth up to the boundary, right? So very classical theorem. On the other hand, suppose I don't demand vanishing at the boundary, right? Suppose that all I know is that I have a solution of this elliptic equation in the interior and it's bounded, or maybe it even blows up at the boundary. Well, what this theorem is saying is that there's always an expansion, but these could be distributions. These AJs and BJs could be distributions. So for example, if I have a solution which is L infinity on the boundary, then A0 is an L infinity function. A1 is going to be a derivative of an L infinity function, so it becomes a more and more singular distribution. But you have an expansion. So it seems a bit weird, and these are not pointwise expansions, but they're very useful nonetheless. Okay, so here are two examples, and I'll stop. So if I take a conformal, so I take MG conformally compact. Okay, I take this operator. So this is the Laplacian plus a spectral parameter. Okay, and I take solutions of this equals 0. It turns out that the initial roots here are x to the initial roots are s and n minus 1 minus s. That's sort of why I write it like this. Okay, so what that says is that any solution like this is going to look like x to the, well, let me write it in the following way, n minus 1 minus s plus j, aj of y, plus the sum x to the s plus j times bj of y. Now, if I'm in the, so here's the s plane. The critical line is the real part of s is equal to n minus 1 over 2. And if you studied analytic number theory, that's a deeply significant line. If you're to the right of this line, that means that this is the big guy, right? So n minus 1 minus s this is a more singular term than this term. Okay, so as Alice pointed out the other day, I can specify, so here's a theorem, I can specify a0 of y arbitrarily. Okay, then b0 of y is determined by a Dirichlet-Neumann operator. So b0 of y is going to be something called capital S of little s times a0, and this capital S of s is a pseudodifferential operator of order 2s minus n. Excuse me, of order 2s minus n? Yeah, 2s minus n. 2s minus n plus 1. Okay, so this is a so-called scattering operator. The special case is when s is equal to n minus 1 over 2 plus I mu, right? Then n minus 1 minus s looks like n minus 1 over 2 minus I mu. And for those of you who are aficionados of the Helmholtz equation, what I'm saying is that you have a solution that looks like x to the n minus 1 over 2 plus I mu, plus another term that looks like x to the n minus 1 over 2 minus I mu. And this is like the classical Sommerfeld condition. So I have waves which are oscillating in the opposite direction. I can specify this guy and I get that. That's the really classical scattering theory that you were studying at Toronto 100 years ago. Okay, so I think I'd better stop here. But just to say that, so in this theorem, and so this whole theory I developed about 30 years ago now, 35 years ago. And so one of our original theorems I did in my thesis really was the analytic continuation of the resolvent of this. And there's a really interesting story there, which I won't say anything about. But then this sort of higher regularity theory. So this was there was a series of papers in the early 90s that this was all developed. So this is sort of where the scattering theory came from. So maybe I'll stop there. And where I'm going to pick up on tomorrow is describing in detail the case where I have this Caprelli-Silvestri operator, L sub s, and I have data with sort of a jump on some interface here. So I'm going to have some be talking about fractional Laplacians on this interface. Excuse me? So L sub s is defined up here. So that's it's like X, except for in this case it's T. and then there's some interface down here. And so that's going to introduce a new singularity into the problem, which I'll talk about. So, okay, forgive me for going over a few moments. Yeah.
Do you know something of this coefficient can be computed in some particular cases? Is there a
The B0 is like? Or
AJ and BJ?
so yeah, so what you can do is the following. So AJ you can A0 you can fix.
Yes.
Okay? And then B0 is globally determined. So it's like a Dirichlet Neumann operator. Once you know A0 and B0, then all the rest are locally determined by those guys. So the point is that B0 is global in terms of the choice of A0. Then all the rest are determined just as derivatives in terms of the leading guys. And you know, they're easier not to compute, but they're just kind of a formal computation. So they're not interesting in a sense. So for example, one thing that's true is if A0 is equal to 0, then B0 is necessarily smooth, and all the coefficients are smooth. If A0 and B0 are 0, if both leading coefficients are 0, then all the coefficients are 0, which doesn't say the solution is vanishing, it says that it vanishes in infinite order. It has no no terms since asymptotic expansion. Then in fact there's a unique continuation theorem of infinity, which says that in fact the solution is 0, but that's a whole separate theorem.
This is also part of your resolvent operators, further 7.
Yeah, I mean this is all sort of part of that package
Special
like this.
case of
Yeah.
resolvent.
That's exactly right.
Other questions? Just a second.
Yes, you can. Yes, absolutely.
Sí, bueno. Gracias.